Hello everyone, my name is Pallavi. The topic of my presentation today is nanophotonics. Here I have outlined my topic under various subheadlines which can be seen on the screen. So, what is nanophotonics? Nanophotonics is a field that focuses on the study and manipulation of light at the nanoscale level, with the goal of developing new technologies that have a wide range of application in fields such as communication, computation, sensing, and energy conversion. The field combines principles from nanoscience, photonics, and material science to understand and control the interaction of light with material or matter at the nanoscale. The concept of nanophotonics has been around for over a century, with early researchers investigating the optical properties of materials at the nanoscale. However, it wasn't until the development of nanofabrication technologies or techniques in early of 1980s. Let's see the fundamental principle on which the nanophotonics is based on. Light interacts with matter in a number of ways, including absorption, reflection, and transmission, depending on the property of object and the wavelength of the light. Absorption occurs when light energy is absorbed by the object, causing the object atoms or molecules to vibrate and heat up. This can cause the object to change color, as some colors are absorbed while others are reflected. Reflection occurs when light bounces off the surface of an object. The angle of incidence of the light determines the angle at which it is reflected. Transmission occurs when light passes through an object without being absorbed or reflected. This can happen when the object is transparent, like a window or a piece of glass. The interaction of light with matter is complex and depends on a number of factors, including the property of the object, the wavelength of the light, and the angle of incidence. Understanding this interaction is critical to develop new technologies in fields such as optics, material science, and nanophotonics. See the nanoscale structures and materials. It exhibit unique property that makes them highly suitable for use in nanophotonic application. At this scale, the interaction between light and matter is governed by quantum mechanics, leading to novel optical properties that are not observed in bulk materials. One example is plasmonic resonance, which arises when the free electrons in the material are excited by incident light. This resonance can lead to enhanced light matter interaction and enable the manipulation of light at the sub-wavelength scale. Another advantage of nanoscale structures and material is their high surface to volume ratio. Since a large portion of atoms in these structures are located near the surface, they are highly sensitive to change in their environment. This sensitivity can be harnessed to develop highly sensitive sensors that detect changes at the nanoscale. Furthermore, the small size of nanoscale structures and material make them flexible and tunable. Researchers can tailor their optical properties by varying their size, shape, and composition. This flexibility can be used to create advanced materials such as metamaterials and plasmatic materials that have unique optical properties and can revolutionize the fields such as sensing, imaging, and communication. In summary, the unique size-dependent optical properties of nanosensor or nanoscale structures and materials, combined with their high surface to volume ratio and tunability, make them highly suitable for nanophotonic applications. Let us now see some fabrication techniques used in nanophotonics. One commonly used technique in nanophotonics is lithography, which involves the transfer of a pattern onto a substrate using a mask. The mask is designed to have openings in specific patterns, and the substrate is coated with a photosensitive material. The mask is then placed over the substrate and exposed to light, which causes the photosensitive material to become more or less soluble in a specific solvent depending on the pattern of the mask. The exposed area of the photosensitive material are then removed using a solvent, leaving behind a pattern substrate. The size of the pattern can be controlled by adjusting the wavelength of the light being used and the resolution of the mask. Chemical vapor deposition is another popular technique for fabricating nanomaterials. In this technique, a precursor gas is introduced into a chamber where it is heated to high temperatures. The precursor gas then undergoes a chemical reaction leading to a formation of a thin film on a substrate. The size and composition of the film can be controlled by adjusting the temperature, pressure, and flow rate of the precursor gas. Atomic layer deposition is a technique that allows the deposition of a material on atomic layer at a time. In this technique, the substrate is exposed to a precursor gas that reacts with the surface to form a single layer of material. The process is repeated for each layer, leading to the growth of a thin film with precise control over its thickness. Electrospinning is another technique used to fabricate nanoscale fibers. In this technique, a polymer solution is placed in the syringe and subjected to a high voltage. The voltage causes the polymer solution to form a charged jet that is then collected on a substrate, forming a fiber. The diameter of the fiber can be controlled by adjusting the processing conditions. Let us now see some applications of nanophotonics. One potential application of nanophotonics is optical computing, which uses light instead of electrons to perform computations. In traditional electronics, the size of components is limited by the wavelength of electrons, which is much larger than that of photons. Nanophotonic components, on the other hand, can be much smaller, allowing for high computational density and speed. For example, nanophotonic waveguides can be used to guide lights and perform logical operations, and nanophotonic resonance can be used to store manipulating lights. Another potential application of nanophotonics is in optical communication, where it can be used to increase bandwidth and speed. Nanophotonic components such as waveguides and fibers or filters can be used to guide and manipulate light signals, allowing for faster and more efficient communication. In addition, nanophotonic sensors can be used to detect and analyze light signals in real time, enabling faster and more accurate communication. Sensing is another field where nanophotonics has potential applications. Nanophotonic sensors can detect changes in light, allowing for the measurement of various physical and chemical properties such as temperature, pressure, and chemical composition. For example, nanophotonic sensors can be used to detect the presence of specific chemical in the environment such as pollutant or toxins. Energy conversion is another field where nanophotonic structures such as solar cells and light emitting diodes can be used to convert light into electricity or vice versa. For example, nanophotonic solar cells can be more efficient than traditional solar cells as they can capture a broad range of solar spectrum. Overall, the potential application of nanophotonics is vast and various. As the field continues to advance, the new materials and fiber techniques are developed. It is likely that even more application will be discovered soon. Let us now talk about the future scope. Nanophotonics is a rapid advancing field with emerging research areas and promising applications, including quantum optics. Nanophotonics can play a significant role in quantum optics by enabling the generation, manipulation, and detection of a single photon. This is essential for developing quantum computing and secure communication systems. For instance, nanophotonics structures such as quantum dots and nanowires can be used as a single photon source or detectors. Nanoscale spectroscopy can enable the development of new technologies in the study of optical properties of materials at the nanoscale. This allows researchers to analyze the property of individual molecules and atoms, leading to a better understanding of electrons and optical behavior. For instance, nanophotonic structures such as nanocavity and nanoplasmonic antennas can enhance the sensitivity of the spectroscopic techniques. Nanophotonic sensors have numerous potential applications too, including the detection of small molecules, toxins, and biological agents. These sensors can operate in real time and with high sensitivity, making them ideal for a range of applications in biomedical, environmental, and industrial settings. For instance, nanophotonic structures such as photonic crystals and nanowires can be used to detect changes in reflective index or resonance frequency. Nanophotonic metamaterials have unique optical properties that can be engineered to interact with light in new ways. These materials can blend light around an object, create negative reflective indexes, and produce invisible clocks. This has potential application in imaging, clocking, and sensing. For instance, nanophotonic metamaterials can be used to create super lenses that enable images or imaging below the diffraction limit. In summary, nanophotonics has promising application in a wide range of fields, including quantum optics, nanoscale spectroscopy, nanophotonic sensors, nanophotonic metamaterials. These emerging research areas are likely to lead to new discoveries and application in the future. Let us address some challenges and limitations of nanophotonics. One of the major challenges in nanophotonics is the scalability. While current fabrication techniques are capable of producing nanophotonic devices, they are often limited in their ability to produce these devices on a large scale. Another challenge in the field is related to the fabrication of nanophotonic devices. Fabrication techniques require precise control at the nanoscale, making them more complex and expensive compared to the traditional fabrication techniques. Many of the techniques used to produce nanophotonic devices are still in experimental stage and not yet fully scalable. Cost is another significant challenge associated with nanophotonics. The complexity and precise or precision required in the fabrication process meant that the cost of the producing nanophotonic device is high. This makes it difficult to make these devices affordable and accessible in widespread. Integration with existing system is also a challenge in nanophotonics. Many applications requires integration with other systems, such as electronics and optics. Achieving seamless integration with other technology may require additional development and optimization. Finally, the availability and cost of suitable materials for nanophotonics applications can also be a limiting factor. In conclusion, or to summarize, the nanophotonics is an emerging field that focuses on interaction of light with matter at the nanoscale. We discussed the unique properties of nanoscale structures and material that make them suitable for nanophotonic applications and the various fabrication techniques that are commonly used. We also explored the diverse application of nanophotonics, including optical communication, computing, sensing, and energy conversion. Additionally, we touched some of the emerging researching area and promising applications such as quantum optics and nanophotonic sensors. However, we also acknowledge the challenges and limitations that exist in the field of nanophotonics, including scalability, fabrication, cost, and integration with existing systems. Overcoming this challenge will be crucial in realizing the full potential of nanophotonics. That's it from my side. Thank you.